Volume of sphere the pi r cube. What?
4 by 3. So actually the volume of the cube is given by what? Just to
4 by
recap,
3.
what we did was previously we considered a Maxwell distribution, which was written in terms of what? C square. But the thing which is sitting over here is in terms of du, dv, and w. Now this is basically your volume of that small element. Now what we were doing was, so what is a volume of sphere? Volume of the sphere can be written as 4 by 3 pi r cube. Is it clear? Because this is the volume of the sphere. And what is the area of sphere? Is this the area of sphere? Can you hear me, everyone? Are you being able to hear me?
4 pi r square, sir. Area of sphere.
4 pi r square.
अम्बो सर तपाईँ लेखेको पनि भर्खर आउँदैछ नि
Now is it okay?
Yes, sir.
Is it, the volume of sphere is given by 4 by 3 pi r cube. The area of sphere is given by 4 pi r square. I think this point is clear. Now how to get from volume to area? What you do is basically take a derivative of volume with respect to radius or r as variable. So what will be d by dr of 4 by 3 pi r cube? This is 4
by 3 by the निस्किन्छ त्यहाँदेखि 4. Yes, sir.
You'll exactly get the area of a sphere. So can I write a small volume dv as 4 pi r square dr?
Yes, sir.
Okay. Now similarly over here, du, dv, dw will give you a small volume dv, which can be written as 4 pi. What will be the radius? No, this is slightly tricky, or when you plot in a velocity space, your radius will be given by what? C square. Clear? So that's why it will
Yes,
be
sir.
4 pi c square dc.
C square dc.
So finally, you have an expression for dn, the number of particles which is present at this small volume is dn can be written as a cube n e to the power negative bc square dc. This is basically your Maxwell's distribution law. Now this law is very important. Now everywhere you'll start using this law. There are many. For a classical particle, for ideal gas, you'll just use this kind of distribution. Let's say you have a box full of particle. How it is distributed? Because they keep on moving randomly. They move in all the direction possible, in all the possible direction. But what will happen is they will have a certain kind of distribution, which is exactly this. Clear? Now, till now, do you have any questions? Any question? A, we have defined it previously. We found it previously. By using what? By normalizing this, or by integrating both sides actually. from negative infinity to infinity. From here, we found, because this is basically, if you have a box which is of size, which can be distributed anywhere, then the total number of particle will be what? N. This I think we have evaluated yesterday. From here, I think we have evaluated this integral. This is what this is basically. It can be found by using what here? Gamma function. First we did was we changed the limit from 0 to infinity, which will give you what? Twice, because this is an even function. So a cube twice a cube from 0 to infinity e to the power negative bc squared dc is basically 1. Now what you can do is let c square is equals to what? Let's consider bc square equal to z. Now bc dc will be what? Dz. Now taking derivative on both sides. This is, I'm using substitution method. And basically what? Your dc will be dz by bc. But c is already sitting over here, which can be substituted from here. C is basically what? Root of z by b. So dc will be how much? How much you get? B will go over here, z will sit over here, root is sitting over here into zz by b. Or you can write this in this manner, dc is equals to, because this is over here, 1 by root of bz dz. Now you substitute this over here. Twice a cube integration of 0 to infinity e to the power negative z, it will be dc will be dz by root of bz. One more thing, we forgot the most important quantity actually. Hatterika. Do you remember what did we forget? This 4 pi c square we have forgotten. So there will be 4 pi c square, it will be sitting over here. I'm extremely sorry. 4 pi c square. Writing in terms of c, you'll get an additional term like this. Okay. So in addition to that, we had what? 4 pi c square dc. Over here, we have 4 pi c square dc. 4 pi c square dc. We can take this 4 pi common outside, because this is a constant outside the integral. And over the c square, we can substitute c square by what? Basically, your z by b. In addition to that, we have what? Z by b into dc. Now you have taken integration of this. B is constant, so you can take it out. So it will be what? 4 to the 8 pi a cube b to the power 3 by 2. I've taken everything 0 to infinity. This is root. This will cancel with z to the power half will sit over here, e to the power negative z dc. And basically this quantity which is sitting over here is gamma 3 by 2. This is basically a gamma function, or for this is half root pi, which will give you, or basically this is what, half factorial, which will give you what, half root pi. Both thing, either way it's fine. So finally you'll end up with what, 8 pi a cube b 3 by 2 into root pi 4 is 8, and you'll end up with what, this is equal to 1, but this on your right hand should be equal to 1. So after that you have to evaluate a. For pi will be given by pi 3 by 2 b to the power 3 by 2 into a cube is basically 1. So this will give you what, a cube will be p 3 by 2 divided by 4 pi 3 by 2. Or basically a will be what, b by 4 pi 3 by 2 3 by 2 to the power 1/3. Now this is basically a constant a. Is it clear? This is just a mathematical problem. This nothing important is over here. You just what, you are just evaluating the constant by using this normalizing condition, or basically for a time, or what do you call over here is by knowing the total number of particles. Which will give you a equal to root of p by pi to 1/4. Actually this one, from here you have to evaluate again what, b. A you have already evaluated, b you have to evaluate. For a time being, most important thing is this constants are just constant. What you really need is that a distribution is what, Maxwell's distribution is of this kind, which is centered at what, at particular value of c. For different c it may increase, for different, because it depends on different your energy or your different kinetic energy, because it's proportional to c square. Is it clear till here?
Yes, sir.
Okay. Now, apart from that, this is just distribution. This is the kind of distribution for a given particle. If they are placed in a box, they are distributed in the certain manner, and remaining some other things. This is just a mathematical normalization and all, which is not important. The main thing is for a given particle is exactly described by what, for ideal gas, by your Maxwell's law. Clear? Now today we'll talk about what here, mean free path. But before that, I think we have to discuss something regarding your Van der Waals equation. Have you heard about? Critical,
Yes, sir.
critical pressure.
Chemistry must make it.
In chemistry, you have heard. So what is the Van der Waals equation?
Bullion.
Actually, first we did for a ideal gas. Ideal gas, the relation was pressure times volume equal to RT. It's proportional to temperature. nRT or RT, nKT, something. Yeah. This was for your ideal gas. This is how your ideal gas behave, how their pressure, volume, and temperature are related to each other. For a real gas,
Yes, sir.
for real gas, this is not the case. Only at a particular regime, what it follows your ideal gas equation, but for the real gas, what it does not behave as told by your ideal gas equation. So what Van der Waals did was, what did he do? he made some corrections. Do you all remember pressure correction and volume correction? This is an ideal gas or a perfect gas equation, which is not obeyed by a real gas. Particularly at what? A high pressure and low temperature. At high pressure and high temperature, it does not follow your what? Your perfect or ideal gas equation. At ordinary temperature and pressure, the deviation is small. If you use the law of ideal gas for a real gas, for a room temperature, it varies, but it varies small. The variation is small. But at high pressure and high temperature, what? The variation is substantial. So you cannot use this ideal gas equation at all. Clear? In the derivation of a perfect gas equation on the basis of kinetic theory of gases, there were certain assumptions which do not hold for your real gases, because the ideal gases we started with certain assumption which does not hold for your real gas. First is the size of the molecule is negligible. First was here, size is negligible, but which is not a case for your real gas. And second is the force of intermolecular. The second thing, as you have all said, the interaction between each molecule is not allowed. But in real cases, what these interactions are also allowed. Reactions are allowed. Clear? Is it clear? But in practice, in reality, at high pressure, the size of the molecule of the gas becomes what? Significant and cannot be neglected. Clear? Because at high pressure, what will happen? This molecule will start coming closer to each other, and what? The interaction between this molecule also becomes important. So this assumption does not hold good for your real gas. So that's why your ideal gas equation has to be what? Modified accordingly. Clear? So this was done by your what? Your Van der Waals. By Van der Waals. So the Van der Waals equation of state, he made two corrections. What should be the two correction? What should be the two correction? One should be the correction in what? One should be made in a correction in volume, because the size is not negligible now. This is one first correction, and second correction should be done in what? In pressure. Because now the interactions are also allowed. Clear? Is it clear? Now he added
Yes, sir.
certain quantity for the pressure, which was what? Given by A by V square, where basically A is here constant. Constant. This is here pressure correction. Pressure correction. And for the volume correction, what did he do? He added some quantity, which is V minus B. This is here. Now V went to this, a pressure went to this. This was for your ideal or ideal gas. This was for your real. For ideal gas, P is P, V is V. For real gas, P went to this and volume went to this, where V is also a constant. Van der Waals constant is Van der Waals constant. So here, equation for real gas will be what? Because we know for the ideal gas it was PV is equals to RT. Now for real, P should be replaced by what? P plus A by V square. And volume should be replaced by what? V minus P to R. Now this is the equation for your real gas. This is how he made a correction. So after that, you were able to make a correct prediction for your real scenario. Is it clear? Is it clear?
Yes, sir.
So why the correction were needed? Because for at high pressure and at high temperature, what they did not behave according to your ideal gas or a perfect gas equation. So that's why Van der Waals made some correction. Basically, he made a correction to your pressure and volume, which accounted for this kind of, which accounted for what? This changes, and that's why we were able to correctly predict the behavior of a real gas. So we'll take a small break, and then after that we'll continue.
Yes, sir.